Here we're given polynomial equation x to the fourth minus 6x cubed plus 12x squared minus 8x equals 0. And we're asked to find all the roots. It says to use the different properties that we know, the Descartes' rule of signs, the rational zero theorem, the theorem on bounds, as aids, A-I-D-S, aids in finding all the roots. Well, I'll use just what I need and nothing more. I'm just trying to find the roots. So the first thing we're going to do is factor this guy. So we see there's a common factor in all the terms of x. So we pull that out, set each of the factors equal to 0, and then we're going to solve. Okay, so we get x equals 0, which is one of the roots, and then we also get x cubed minus 6x squared plus 12x minus 8 equals 0. Now let's work just on that factor. It's a degree 3 polynomial, and we'll call f of x the x cubed minus 6x squared plus 12x minus 8, and we'll count the number of sign variations. It starts positive, changes to negative, changes to positive, changes to negative. That's 3 variations. So that means there's going to be 3 minus 0 equals 3, or 3 minus 2 equals 1 positive real roots, either 3 or 1 positive real roots for that factor. Let's find f of negative x. That's equal to negative x cubed minus 6x squared minus 12x minus 8. Let's count the number of sign variations. There are no sign variations in this, so there are 0 minus 0 equals 0, negative real roots. Okay, either 3 or 1 positive real roots, and then exactly 0 negative real roots. So we're going to make a table. Remember, we're just finding the roots for the second factor. Here's the positive real roots. We're going to add the negative real roots. We're going to add the imaginary roots, and they will total the degree of the polynomial, which is 3. Now, before we get too far into this, I want you to remember positive real roots and negative real roots leaves out one type of real root, the 0 real root. When x is equal to 0, it's neither positive or negative. Well, we found a 0 real root when we factored the common factor x out of the original problem. That gave us x equals 0. So we have already found one of the 4 roots for the original problem. We're in the process of finding the other 3 roots for the second factor. Okay, so we called f of x the second factor, and we found that there's going to be either 3 or 1 positive real roots there, and no negative real roots. Let's continue. Let's set this up. There's either 3 or 1. They're going to total 3, and there's going to be either 3 positive real roots plus 0 negative real roots, and that would require 0 imaginaries to total 3, or 1 positive and 0 negative has to total 3, so that would give us 2 imaginary roots. I want you to notice that there are a possibility of 0 or 2 imaginary roots, and indeed that has to be an even number since they always come in pairs. Imaginary roots always come in pairs. So this chart, it actually looks good for Descartes' rule of sign. We're either going to end up with 3 positive real roots, and that's going to be all for our second factor, or we're going to have 1 positive real root and 2 imaginary roots. Okay, now in order to find these roots, well, I would first try to, of course, factor. That's the first thing I did try to factor, but I don't know how to factor x cubed minus 6x squared plus 12x minus 8 equals 0. So I'm going to use the rational zero theorem. I'm going to come up with a list of rational zeros, p over q, using the rational zero theorem. And then I'm going to test them with synthetic division. So the top has to be plus or minus the factors of the constant coefficient 8. So on the top, it's going to be either 1, 2, 4, or 8. And the bottom is going to be the factors of the lead coefficient. That's the number 1 that's multiplying the highest power of x. Those factors are just 1. So the list is positive or negative 1, 2, 4, or 8. Now, it says positive or negative, but we already determined using Descartes' rule of sign, there are not going to be any, there will be no negative real roots. And there's no reason to test any of those negative roots, rational roots. We're going to just test the positive ones. And we're going to do that using synthetic division. We're going to synthetically divide and look for a zero remainder. If there's a zero remainder, we know the number we divided by will be a root. So starting with the first positive number, 1, take the coefficient of the second factor, which is 1, negative 6, 12, and negative 8. Synthetically divide by making a line and bring down the first number. Multiply 1 times 1 is 1. Add. You get negative 5. 1 times negative 5 is negative 5. Add. You get 7. 1 times 7 is 7. Add. You get negative 1. That told us nothing. We were hoping to get a zero remainder so that we'd know that x equals 1 is a root. It didn't happen. We had a remainder of negative 1. In addition to that, we were hoping possibly of getting all non-negative numbers on the bottom when we synthetically divided by a positive number, so we'd have an upper bound and we'd know how high we can go with these roots. That didn't happen either, so we found nothing. Let's go to the next number in the positive list, the number 2. Synthetically divide the second factor by 2. So we have 1, negative 6, 12, negative 8. Bring down the first number, multiply, add, multiply, add, multiply, add. Oh, there you go. Happy face. That's a 0. We got a 0 remainder, which implies that the number we were dividing by, 2, is a root of the polynomial. We're going to use that to continue our factorization of the original problem. First, we factored out an x, and then we're going to have x minus 2 because we just found that root. And for the rest of it, I'm going to use the coefficients on the bottom of the synthetic division, which were 1, negative 4, and positive 4, and write 1 degree lower than the third power, x squared minus 4x plus 4. Then I'm going to factor that second degree factor by guessing x minus 2 times x minus 2. And look at, I have repeated factors. I actually have x times x minus 2 to the third power equals 0. So look at this. What have I found? I found x equals 0 as a root. I found that at the top. I also found that x equals 2 is a root, the number being subtracted from x. But it has multiplicity 3. Okay, so think about this and compare our answer to the table. The table said we were going to either get 3 positive or 1 positive real roots. We got 0, which doesn't count as positive or negative, but we did get the number 2. That's a positive real root, and it counts 3 times because it has multiplicity 3. So we got the situation where we have 3 positive real roots, and that's all from that second factor. So it was exactly what we expected. What you will notice is that we didn't use the theorem on bounds, and that is not a problem. We just use whatever we need. It turned out that we weren't able to find a bound. Now, if we had synthetically divided by 1, 2, 3, 4, eventually when we got to 5, we would have found a root. Let me show you. Or 6. 6 would have given us an upper bound. And not a root, but an upper bound. So if we were using that, we could see if we synthetically divide by 6, it's going to give us, let's see, 1, negative 6, 12, negative 8, synthetically divide, and on the bottom we'll get, bring down the 1, and then, let's see, 6, 0, 12, and then 6 times 12 is 72, 72, add, you get 64. So I want you to notice that on the bottom we have all non-negative numbers because the 0 counts as a positive or negative, whichever you choose, in the bottom. So it's 1, which is positive, 0, which we call positive, 12 is positive, and 64 is positive. At that point, I would say, hooray, look what I found. I found x equals 6 is an upper bound, which means we're not going to find any root larger than x equals 6. But we already knew that because we already found all the roots. They were 0 and 2. So that I wouldn't have even gone that far. I was just testing all the p's over q's, the 1, 2, 4, 8. I would have skipped right over 6. By the time I got to 8, I would have gotten an upper bound because I can see if I did the synthetic division, I would get all non-negative on the bottom. But it doesn't matter. You don't have to use everything. You'll notice the order and how I did this. First, I tried factoring. You should always try factoring first. That might be all you need to do to find the roots. Next, I said, well, let's figure out Descartes' rule of sign and see how many positive real roots, negative real roots, imaginary roots, and total roots we're going to possibly get. And then, most important of all, what are the rational zeros p over q that I can synthetically divide and look for zeros? Now, it was good to do Descartes' chart first because it told me, in this case, I didn't even have to look at the negative numbers in the list of p over q because there are no negative real roots. So it saved me some time. The answers are x equals 0, x equals 2, with multiplicity 3. That's a total of 4 zeros, which is exactly what I expected.